Okay, this is part two of Hardy-Weinberg. Last class was cut short, so we're going to pick up where we left off. Here we go. So I left off with example number one. In a population of 17 students, 12 students have dark hair and 5 students have light hair. Dark hair is dominant to light hair. Okay, everybody? Now, this next part comes to the critical thinking aspect of it. Of these total of 17 students, I have 12 that have dark hair and I have 5 that have light hair. Can you tell me what are the possible genotypes of students that have the dark hair? Sophia, could you tell me, like yourself, you have dark hair. Can you tell me a potential genotype for these students who have the dark hair? They could be homozygous dominant, sure. Anything else? They could be heterozygous. Okay. Um, Ivory, can you tell me a potential genotype or genotypes for students that have the light colored hair? Are there any other possibilities? There are not. Very good. So this gets me to my first point, everybody. And if you can remember this, this will avoid you a whole lot of grief. It's something very simple, but it can often be overlooked. Here we go. Simply because an individual may express a dominant phenotype, in this case, dark hair, they do not have to have the homozygous dominant genotype. They don't have to have it. And these two girls are 100% correct. Simply because Sophia here up in the front row has dark hair, that's a dominant trait in humans. I think we all know that by now. That does not automatically mean that she is homozygous dominant. She could easily be heterozygous too, but here's the problem. I don't know. I don't know which one she is simply by looking at her. I could ask her questions about her family, her mom, her dad, siblings, and I could probably eventually figure it out. But just sitting here looking at her, no one can tell, and neither of you can tell me either. Like, can you tell by looking at my dark hair if I'm homozygous dominant or heterozygous? No, you can't. So you can't just guess. On the other hand, with what Ivory said, these 5 kids that have light hair, they're homozygous recessive, or Mendelian genetics is a bunch of garbage. And I'm inclined to say the former, not the latter. Maggie back there is homozygous recessive, or Gregor Mendel is the biggest liar that we've ever seen. She's homozygous recessive. So I want to make that other point here. When an individual expresses the recessive phenotype, they must be homozygous recessive. Okay? If you can remember those two, you'll do pretty well. So, with that being said, here's your first problem, part A. Calculate the frequency of homozygous recessive. Now, I cannot assume that all 25 of you know how to do this math. I've got to know for sure that all of you guys know how to do it. There's going to be no assumptions. There's going to be no guessing. I need to know. When I'm asking you to find the frequency of homozygous recessive, let's get something down first. John, when we're talking about homozygous recessive, what variable from both Hardy-Weinberg equilibrium equations does the frequency of homozygous recessive represent?
Q.
Nope.
Oh, Q squared.
We need to find Q squared in this problem. So, which trait is the recessive trait here? Is it the dark hair or is it the light hair? It's the light hair. And what did Ivory correctly say the genotypes of these 5 people must be? So 5 out of 17 people are what genotype? 5 out of 17. Here's how you find frequencies, guys. This goes to what I was saying a moment ago. I need to know. And if you don't know, now's your time to learn. Welcome to school. In order to find the frequency of homozygous recessive, which is Q squared, you have to take the number of individuals that are homozygous recessive, in this case, 5. And you have to divide it by the total number of individuals, which was how many? 17. So what is 5 divided by 17? 0.294. That right there, everybody, is the variable, or excuse me, is the frequency of homozygous recessive. Now, the first thing I want to help you avoid is I do not want your brain to take you down a dark dead end. You do not have to square that number. That number is Q squared. You don't need to do 0.294 squared. No. If you were to think that, oh, I need to square it, then what you're suggesting is 0.294 is Q. It's not. 0.294 is Q squared. Second thing I like to say, the number one misconception in this entire gobbledygook that we call Hardy-Weinberg equilibrium, it's already happened many times today, is students have trouble differentiating Q from Q squared. So some of you might be wondering, wait, why isn't that Q? Here's why. Look right here. According to the from yesterday, P is the frequency of the dominant allele. Q is the frequency of the recessive allele. If you were to conclude that 5 divided by 17 equals Q, and not Q squared, here's my rebuttal to that. Aren't some of the blonde-haired people containing a recessive allele? They could be. They could be heterozygous. And you're leaving those recessive alleles out. Q is supposed to represent the frequency of all the recessive alleles. If you're going to do 5 divided by 17, you are completely leaving out those group of people within the 12 dark-haired folks that could be heterozygous, and they contain a recessive allele. So in order for someone to show a recessive trait, like Maggie or Ava, they had to inherit a recessive allele from their mother and a recessive allele from their father. We call that a genotype. One recessive allele, genotype. You don't just need one recessive allele. You need the genotype for it. So that is Q squared. Are there any questions? Okay, let's go to part B then. I now would like you to calculate the frequencies of the dominant and recessive alleles. I'm going to help you out with this first example. Then when we get to examples 2, 3, and 4, then I'll let you start to work on your own. So I want to find the frequencies of the dominant allele and the recessive allele. Let's see. Based on your notes from yesterday, Leo, what variable represents the frequency of the dominant allele? That is correct. And while you're at it, can you tell me what variable represents the frequency of the recessive allele? That is correct. You guys are being asked to find P and Q here. Now, part A is going to help you out. On part A, you found Q squared. Which variable for part B do you think would be the easiest to find now that you do have a value for Q squared? Q would be the one you want to go for. So how do I find Q from Q squared in part A? Bingo. Q equals the square root of Q squared. Now, before I do go any further, hear me out. You could potentially have one of these types of problems on an FRQ. And up to this point in the class, when you've been doing FRQs, you've been writing sentences and paragraphs. How do you earn points when you have math problems? You show your work. You have to show your work step by step. And if a party goes, oh, that sounds so tedious, good. Because I'd rather be tedious than hard. You are in the business of earning as many points as you can in an FRQ. And if that calls for you to show your work, so be it. Show your work, show your steps. So Q equals Q squared. Q equals Q equals the square root of Q squared. Q equals the square root of 0.294. Leo, can you tell me what that is using your calculator? Round it to the nearest thousands place if you would. Yep, that's what I got. Great. Now, before I forget, I want you guys to be putting your answers in a box or in a circle so that the grader, like me, or the grader in Philadelphia or New York City, when we mail your AP exams to, don't have to go looking for your answer. They need to be indicated by boxing it or circling it. Okay, so now that we found Q, we're going to go after P next. Now, in the Hardy-Weinberg equilibrium equation, one of them, P plus Q equals 1.0. Guess what? You have Q now. So use that old algebra that you learned in middle school. P plus 0.542 equals 1.0. Subtract 0.542 from both sides. What does P equal? 0.458. There they are. P and Q have been calculated. You have now found 3 out of 5 of the total variables that you could find for Hardy-Weinberg. You have found Q squared, you have found Q, and you have found P in that order. Let's get to the final part. Part C. Calculate the frequencies. Of homozygous dominant and heterozygous. And again, I want to do this one with you. After this, I'm going to have you go more on your own. Let's see. Cohen, what variable from Hardy-Weinberg represents the frequency of the homozygous dominant genotype? Look, check out your notes from yesterday. That would be P squared. And Erica, what variable from the Hardy-Weinberg equations that you learned yesterday represents the frequency of heterozygous? That is correct. 2PQ. Okay. So, let's see. Charlie Nash. Based on information and answers that we have calculated from parts A and B, do we have what we need to solve for P squared? What would you do? P squared would equal what? What math would you do? That's pretty much it, Charlie. So P squared equals what? What's 0.458 squared? I'm talking to Charlie. We need to round that to the nearest thousand. So I got 0.2097. What would that round to? 0.210. There's P squared. And now 2PQ. In order to get 2PQ, you need P, you need Q. Guess what? You found that in part B. So just plug them in. Look at how I show my work here, guys. 2PQ equals 0.458 times 0.542. 2PQ equals 2 times... Hold on. I got 0.248 here. And then 2PQ is going to be 2 times 0.248. I got 0.496. Yes, Adriano. You could, but that may not always be an option. So I wanted to teach you how to do it by the book. All right. You're almost ready. I got one more for you. This is a bonus one. Calculate the number of individuals that are homozygous dominant and heterozygous. I want numbers. I don't want frequencies anymore. Like, I want to know of those 12 people, how many are homozygous dominant? How many are heterozygous? And I need you to round your answer to nearest whole number. Again, I do not want to assume that all of you know how to do this, because that can be trouble. I need confirmation that all of you know how to do this. And if you don't know how to do it, that's why you show up. That's why we do this, so you can learn. So if you recall, 12 people have dark hair. I want to know how many of those 12 are homozygous dominant, how many are heterozygous. So use the information that you got in part C to see if you can do that. Some of you probably know what you're doing. Some of you might be like a little lost, and that's fine. I'd rather you be lost today and figure it out than be lost on your test and have to deal with it. Is anyone here willing to volunteer because they know how to find the number of individuals? Go ahead, Maggie. What do we do? So let's say I want to find the homozygous dominant genotype first. You said that I need to multiply 12 times what? 0.210. Why did you choose 12? So 12 is the total number of individuals with dark hair. Why did you choose 0.210? That's the frequency of people with the homozygous dominant genotype. So 12 times 0.210. I got 2.5. So let's round that to the nearest whole number. What would it be? 3. 3 people are homozygous dominant. And then for heterozygous, we have 12, which is the total number of dark-haired people, times what do we multiply this by? John, do you know? Why'd you choose 0.496, John? What does 2PQ represent? The number of heterozygous individuals. Okay. So I got, hold on a second. Oh, I know what I messed up. Okay. Yep, I messed up. So it should have been 17, not 12. My fault. It should have been 17. That's on me. 17, you got to multiply by the total population. Okay, so 17 times 0.210. This is better. That's going to be 4. 17 times 0.496. This is going to be about 8. What's 8 plus 4? There we go. That's 12. People, so this right here is the total population. And then the 12 circled back there. 12. All right. I think you're ready to be let off the leash here. Let's get to example problem number 2. Oh, before I do that, here's a little reference point. When solving for the variables, try to find q squared first. If you can find q squared first, everything else falls into place. And once you all start to get more comfortable doing this and get pretty good at it, you'll be able to find the other 4 variables in probably less than 60 seconds. So here's the order that we found things. First, you guys identify q squared. Next, you found q. Then you found P. And after you find P, it's really up to you. You could go for P squared next, or you could go for 2PQ. Either one, you have the information to find both. Personally, I go for P squared first, but that's just me. But you do need to go in this order for the first three. Q squared, Q, and then P. Okay? So let's see if I can stump some of you. Here we go. Example problem number 2. At Plant High School, the frequency of the dominant allele for eye color is 0.9, and the frequency for the recessive allele is 0.1. I'll give you a moment to copy that. Here's your task. Calculate the frequency of homozygous dominant, heterozygous, and homozygous recessive. I'm going to pause the video. I'm going to pause the recording of the video. So if you're watching, just pause the video on your computer, and then I will resume it once everyone has been given time in class to work on it. Okay, so let's get a few things established before I go about solving this. With the information that you guys were provided in the prompt, I had the frequency of the dominant allele is 0.9. What variable from Hardy-Weinberg is the frequency of the dominant allele meant to be? P. So in this problem, you are given P equals 0.9. You're told that. You just have to know, or you have to be able to recognize that. Also, you were told that the frequency of the recessive allele is 0.1. What variable from Hardy-Weinberg does the frequency for the recessive allele mean, or stand for? Q. You're given Q. You just have to be able to acknowledge that. You have to be able to recognize that. So now that you have that information, let's go through part A. I want to find the frequency of homozygous dominant. What variable is homozygous dominant? P squared. Now, in these notes I put up here, when solving for the variables, try to find Q squared first. You don't need to do that. Your life has been made so much easier on this problem. You have P. So P squared is simply 0.9 squared. So P squared is 0.81. Circle your answer. What variable in Hardy-Weinberg is, almost said it, is heterozygous? 2PQ. So plug in what you were given in the problem. 2PQ equals 2 times 0.9 times 0.1. Show your work. 2PQ equals 2 times 0.09. 2PQ equals 0.18. And then lastly, homozygous recessive. What variable does homozygous recessive get represented by in Hardy-Weinberg? Q squared. Well, you guys were given Q on the prompt, so Q squared is simply going to be 0.1 squared. Q squared is going to be 0.01. There are your three variables. And to make sure that they do in fact add up, and this is all in Hardy-Weinberg equilibrium, P squared plus 2PQ plus Q squared should equal 1.0. Now, you can probably do this in your mind, but we need to make sure. Is 0.81 plus 0.18 plus 0.01 equal 1.0? Yes, it does. So it checks out. Everything fits. The numbers don't lie. Are there any questions on example problem 2? If you're having confusion, this is the time and place to ask. Okay, then let's move on to example 3. Step it up a little bit. At the Soho Chipotle, the corn bucket in the serving line has 1,000 kernels of corn. Period. In corn, yellow is dominant to white. The bucket contains 910 yellow kernels and 90 white kernels. I'll give you a moment to catch up before I start giving you your problems. Okay, here's part A. Calculate the frequencies of the dominant and recessive alleles. I'll give you a moment to finish writing that down. Then on the YouTube video, I'm going to pause the recording. So if you're watching this at home, just pause the video, let yourself work them out. And I'll resume the video once the students in class have had a chance to work it out on their own. Okay, so let's get back to this and if confirm if you're doing it right, and if you're confused, I can help you out. According to this information, the first thing I notice is that yellow is dominant to white. That's helpful. John, what's your favorite letter in the whole wide world?
R.
Fine. Good choice. So we're going to say that yellow has the dominant allele and white has the recessive allele. Okay? Now, continuing on in the problem, it says that the bucket contains 910 yellow kernels. What are the possible genotypes of those 910 kernels? They could be homozygous dominant. What else could they be? Do you know how many of those 910 are homozygous dominant? And do you know how many of those 910 are heterozygous? You don't know. It's like, I don't know how many of you brunettes in this room are homozygous and how many of you are heterozygous. I don't know. On the other hand, we got 9 kernels that are white, 90 that are white. What is the possible genotype or genotypes for these 90 white kernels? Homozygous recessive. Oh, wrong letters. So I think we have something here. Remember what I wrote earlier? Try to find the homozygous recessive genotype first. So in this problem, you need to get to the dominant and the recessive alleles, but getting Q squared first can help you along that way. So 90 divided by 1,000 is going to give you Q squared. Now, before I do go any further, I want to help you out and I want to make you aware of something that everybody all day has been messing up on. Kids all day today have been saying 910 divided by 1,000 equals P. And to that, I'm going to say, what about these? You're including recessive alleles in the number that's supposed to be strictly dominant alleles? That's not right. When you have a problem like this, if you can find Q squared first, which is the frequency of homozygous recessive, everything else falls into place. So 90 out of 1,000 is 0.09. That is Q squared. But Mr. Thorson, we're not trying to find Q squared in part A. Yeah? Well, maybe the goal of the game is to throw the football in the end zone, but sometimes you got to have some big passes in between that drive to get you there. This is going to be like a stepping stone to get you to that. So now that you have Q squared, what variable can you go for next? Q. And how are you going to get Q from Q squared? Square root it. Look at how I'm showing my work. Q equals the square root of Q squared. Q equals the square root of 0.09. Q equals 0.3. There it is. The number one misconception that students have in this whole concept of Hardy-Weinberg is confusing Q for Q squared. So I bet some of you probably wrote Q equals 0.09. That's not it. In order for a kernel to be white, in order for a kid to be blonde, they have to have two copies of the recessive allele, not just one. They have to have two. That's why the 90 divided by 1,000 is Q squared and not Q. So we did the square root of 0.09 is 0.3. And now that we have 0.3, let's find P. P equals 1.0 minus 0.3. I think you can probably do that in your head. P equals 0.7. The dominant allele is P, and the recessive allele is Q. We now have both of them. Are there any questions, honestly, that any of you may have about this so far? Joe, Charlie, you too good? Joe, you sure? All right, part B. Calculate the frequencies of homozygous dominant and heterozygous. Oop. Okay, I'm going to pause the recording again. So if you're watching from home, just hit pause on your computer. I'm going to give my class a couple of minutes to work it out. We'll be right back. So homozygous dominant is going to be P squared. You have P, so it should be pretty straightforward. P equals 0.7, or excuse me, P squared equals 0.7 squared. P squared equals 0.49. Heterozygous genotype is 2PQ. Look at how I show my work. 2PQ equals 2 times 0.7 times 0.3. 2PQ equals 2 times 0.21. 2PQ equals 0.42. Any questions on part B? All right, last one that we have time for today. C. Calculate the number of individual kernels that are homozygous dominant and heterozygous. And one more time, I'm going to pause the recording so my students in class have an opportunity to work on it here. If you're watching at home, just hit pause. So here's how you do it. For homozygous dominance, we have 1,000 total kernels. What was the frequency of kernels that were homozygous dominant in this problem? 0.49. So this math's pretty easy because it's 1,000. 49% of 1,000 is 490. 490 kernels are homozygous dominant. And then for heterozygous, 1,000. What was the frequency of heterozygous kernels? 0.42. Pretty easy because it's 1,000. 420. And you were given the number of white kernels in the problem. It was 90. So what is 420 plus 490 equal? 910. Numbers don't lie. All right. We're going to stop the lesson here. I'm going to give you guys one more practice problem tomorrow. It's going to be very different than what you've had today. And then you're going to have an assignment to work on the rest of class for a grade. That is it for part 2.